I've titled this lecture String Theory, but that's a bit of a joke because, as you know, superstrings are the absolute rage in physics and everyone wants to learn them, and they're supposed to be the very secret of the universe itself, what elementary particles are made up of. Well, we're going to do nothing like that. What we're going to take is just an ordinary string composed of masses, atoms, and use Newton's law to derive the wave equation which you saw in previous lectures. So using Newton's laws, we will be able to predict the speed at which information can travel down the string. It will also be an introduction to what is known as wave impedance. This is an interesting concept and we'll come to it shortly. Let's imagine a discrete system of springs and masses. Discrete means made up of different components. It's different from continuous. Now imagine that you looked at a string, an ordinary string. Well, you would find atoms there, and these atoms would be separated by some distance, and there'd be some force acting between the atoms that you could represent with a kind of spring, so that if you moved this atom up or down, it would be pulled back to its original equilibrium position. And of course, it's going to be a system with a lot of atoms and a lot of springs. Well, I'm not going to draw springs. I'm instead going to draw strings. So I'm going to draw it this way. So it's easier actually, which is why I'm going to do it. So I have a lot of these, and you can imagine that there'll be millions and millions and billions and billions of these atoms and the little strings over there. Okay, so let's make a few definitions. Well, each of these particles has mass. So the particle mass is m. M is very small, but there are lots of particles, so this string will have some amount of weight. There's going to be a tension in this string, and the string tension will be denoted by the letter T. Now, T is a force. This string that's between two particles is massless. So we make the assumption, or we make the model, that the string mass is zero, exactly zero. Now what that means is the following. Suppose I have a bit of string like this. If even the slightest force is applied on that, then it will accelerate and it'll scoot off somewhere, which means that no force can act upon a massless string. What that means is that suppose this atom is pulling this atom towards it in this direction with force T, tension T. Then this atom, this one here, is pulling this atom towards it, also with the same force. And so the two forces cancel out over here. There is no net force acting upon the string. So that's a very important thing to realize, that if this is pulling this with some force, then this is pulling that with the same force. And there's no net force in the string. We shall take the distance between masses. So between one atom and the other I sometimes call them massives, sometimes call them particles. Same thing. And I'm going to denote that with the small letter L. L is obviously a distance. Now, we are only going to consider, so we will consider only transverse waves, transverse motion. What that means is the following, that this atom, for example, can move up or down, and similarly, this can move up or down. It cannot move sideways. That would correspond to longitudinal motion, and we can consider that later. But for now, the best thing to do is to think in the following way, that this atom is moving in some kind of a groove. It can go only up and down. So that's what we call transverse motion. Now, we don't have to do it, but we will limit ourselves to small amplitudes. And the reason for that is it makes the mathematics easier. This is the way in which you can get the wave equation. If you go to larger amplitudes, well, maybe you can derive the equation, but then you would not be able to solve it. So this is very much like what you saw in the case of the simple harmonic oscillator, the pendulum. You limit to small oscillations. And so we're going to take these oscillations to be small. Now, in real life, you could have electromagnetic waves, and electromagnetic waves will be oscillations of some kind, we won't go into that now, in which you don't have to have small amplitudes. They can be as large as you want. However, this is what we're going to restrict ourselves to. So this will also, we will not include waves like tsunamis. Tsunamis requires a very different kind of physics. But first one learns simple things in physics and then goes on to more complicated things. Okay, so here we begin our formulation. So here is a straight line, and there are atoms in it like this. So let's draw some kind of an axis over here. This we shall call the x direction. This we shall call the y direction. And now the equilibrium position of this string and of this system of balls and springs or atoms and springs is this. So if you do nothing, they will all be at y equal to 0. Now what if you take one of these, let's say the nth one, and move it up? And let's take two of these. So this is the position, let's call this xn minus 1. Then at a distance small l from this is the position xn, and this is the position xn plus 1. Now we're going to call this height, that is to say the displacement. So this over here we shall denote by yn minus 1, and this will be yn, and this will be yn plus 1 from here to here. So that height, this height, this height, they will all be in general different from each other. Okay, now let's review a number of things. First of all, Newton's law says mass into the acceleration is equal to the net force. Okay. Now, let's focus our attention upon the nth mass over here. So we want the mass into the acceleration of the nth mass. Now, I could write that ordinary derivative d2y dt squared, but I'm going to write it this way. So this is d2yn by dt squared. Now, why did I write it as partial derivative d by dt instead of ordinary derivative? That's because this particle over here can move only up and down like this. And so x is fixed. The position in the x direction is fixed. In the y direction, it can change with time. And now this has to equal to the net force that is acting upon this. So now we want the net force. Okay, so look at the forces that are acting upon this. So this one over here is pulling this particle in this direction. This atom here is pulling it in this direction. So there is we will have to figure out how much net force there is in the vertical direction. You see, we're not concerned about forces in the horizontal direction because I told you that we're not considering longitudinal waves, just transverse waves. Okay, so let's work out now the net force. So I'll have to draw a little diagram like this. So let me draw this one here, and so this one there'll be some angle over here. Let's call this theta 1, and there's some tension T over here. Now remember that this tension is the same everywhere. So the net force we have to calculate now. The net force, which we're going to put on this side over here to complete Newton's equation. So this is going to be equal to T cosine theta 1. And now there is on this one a force that's acting in this direction. Now let's call that. So this is a tension that's acting in this direction, and again there's some angle which is made over here. Let's call that theta 2. Now this is, the projection is downwards, so this is minus T cosine theta 2. Okay, so now let's figure out what is cosine theta 1 and cosine theta 2. Now here you can see that this height over here is y2, is yn plus 1 minus yn. That is to say, so if I go over here, let me try and change a pen. So if I look over here, from here to here is yn, that's the same as this, and from here to here, this portion over here, so this red portion, this will be yn plus 1 minus yn. Okay, so let's draw a little triangle like this. As I said, this distance is always L. This distance here, now we've agreed is yn plus 1, n plus 1 minus yn. And this, so therefore, cosine of theta 1 will be equal to yn plus 1 minus yn divided by this distance over here. So how much is that distance? Well, that's square root of L squared plus yn plus 1 minus yn squared. And now this, you see, we've said that these are going to be small amplitude oscillations. So this side is small compared to this side. And so cosine of theta 1 will simply be yn plus 1 minus yn divided by L. And that is, of course, you recognize that's just the slope of this line over here. So the net force, let's come back over here. This is T into the, let's take T common. So it's yn plus 1 minus yn divided by L. And now let's come over here. Here the slope of this is going to be just the same thing, except it's yn minus 1 divided by L. So that's the net force, and we can put that in over here. But before we do that, this is the slope here. This quantity is the slope of this line. So this is actually the difference of the two slopes. And now if I do the following, so I'm going to write this as TL and write it in the following way. So this is dy by dx. Halfway in between them, so let's say this is n plus a half. Now, n plus a half over here means that it's the slope midway between these 2 points, minus dy by dx here, midway between these 2 points. So n minus half. That's what I mean by there. And there's L over here, so I'm dividing by, so this, what I've done is I've divided by L and multiplied by L. But then you see, this is the change in the slope divided by the distance. So it's just the second derivative. So this is equal to approximately, this is TL into the second derivative of y with respect to x at the position n, so at the center position. And so therefore we have this Newton's law telling us that m d2y by dt squared is equal to TL d2y by dx squared. And now I'm omitting, see, this is true everywhere. It's true at the point, at the center point. It's also true here, true everywhere. And so what we've done is, in the limit where the distance between the points becomes very, very small, in other words, as L becomes smaller and smaller, what we have is a differential equation like this. Okay, now we've actually made a transition by going from the discrete, in which the points are separated by some distance, and now we're making that distance smaller and smaller. And so therefore what we have is the following. We now have a situation where we have d2y dt squared is, or let me write it the other way around. We have d2y by dx squared equals m over L t d2y by dt squared. Now this m over L, remember what m was. M was the mass of each of the atoms or the particles, and L was the distance. Now suppose there are lots of them. Okay, so suppose there are n of these and n of these. You see, I've just multiplied the numerator and the denominator. Now n times m would be the total mass of the particles, of n particles. So this would be the total mass, and n times L would be what? It would be the total length of the string. And so what we have is mass per unit length. And it's we can give that some name. Let's call it rho. So rho would be the mass per unit length of the string. And what we've got now is the equation d2y by dx squared equals, now I'm going to call this thing m over lt as v squared. So just now I've given this definition of v squared as L into T divided by M. Now that looks just like the wave equation. In fact, it is the wave equation. The only little bit of work that we have to do is to make sure that the dimensions are right, that we have not made a mistake in getting the dimensions. Checking dimensions is a very important part of physics. So let's look at the dimensions of this. Okay, so so we write it this way: dimension of v squared. Well, that's L is length, T is tension, and you remember tension is the same as force. Well, how do you get the dimensions of force? Force is mass into acceleration. What's acceleration? Lt to the minus 2. So speed over how fast the speed changes, so that's Lt to the minus 2, divided by m. And now, of course, m and m cancel, and this is L squared over T squared, and that's the same as, well, those are the dimensions of a velocity. And so what we found is that the velocity with which a pulse will propagate is this thing. So this is an important result, that V is the square root of the tension divided by the mass per unit length. And it was done using only Newton's law. So to remind you, all we did was we said, okay, take a mass over here. It can move only up or down. And look at the net force that's acting on it. There'll be a force pulling it this way, a force pulling it that way. Well, one is pulling it up, the other is pulling it down. So we take the difference between the two, and we find that it's the difference of the derivatives, and that's how we got this equation over here. Let's check our mathematics with the animation that you saw earlier as well. Okay, so I'm going to give this a little pulse, and you see that pulse is traveling down, and since this is a string without an end, it's just gone straight through the window. It's propagating now forever and ever. Now, let's look at this again. So here is the pulse. The pulse is propagating. Well, I'm going to increase the tension, and so you remember that the speed v is proportional to the square root of the tension. So if I increase the tension, the speed should go up. And indeed it has gone up. And what if I make it still bigger? Well, you see that it's moving faster. And so the point is that we've discovered that changing the tension changes the speed at which a pulse propagates. Now, of course, that could be a sinusoidal, a periodic wave as well. Now, notice over here, our second point, that this is a transverse wave. Look at each one of these particles. Fix your eye on any one of them. Let's say the green one. They just move up and down, up and down. There's no sideways motion. And so what we did in the derivation applies exactly over here as well. Now there's one other interesting thing that I want to show you. Earlier on we looked at fixed end and we looked at no end. Now I'm going to look at loose end. So here is the last atom, the last particle, and it's modeled with as attached to a ring. So this atom, you can say, moves freely up and down. There's no friction over here. And so let's see what the condition is when a pulse or a wave comes and hits this ring over here. Okay, so let's take a pulse and send it there. Watch what happens. As it comes, what did you see over there? Well, let's do that again. So let me restart. So watch this again carefully. So you see each particle is pulling the other one, and the last one then gets pulled up and then back. Now, equally, I could do this with an oscillation, and you would see this in the same way, perhaps more clearly now. What do you see over here? I'm just going to put this boundary condition in mathematical form for you, but now you can see that this ring is moving up and down, and of course its amplitude is growing. That's because energy is being pumped into this from this wheel over here. But now let's go and look at the mathematics. Let's now reflect upon a problem where one end is fixed and the other is loose. So I'm going to take a string with one fixed end and one loose end. So the loose end you just saw in the animation. So here's a picture. This end is fixed. This end can move up and down. So there's some frictionless rod, let's say. And now the motion that is possible will require that dy by dx be equal to 0 at x equals L. So if this is the distance L, this is x equal to 0, and this point over here is x equal to L. And so what we require is that dy by dx be 0 at this. In other words, the string should be perpendicular. Why is that? Well, let's reflect upon the following. So there was over here, you saw a massless ring. And what that means is that there should be no force acting upon that ring either up or down in this direction. Why? Because if some force, no matter how small it is, acts on a massless ring that can move only in this direction, then it will accelerate the acceleration will be infinite, the speed will become infinite. And so this is why we must have this condition that dy by dx at x equal to L must be equal to 0. Okay, so we now have two conditions. One is that y must be equal to 0 at x equal to 0, and the other is that dy by dx must be 0 at x equal to L. Now, this is going to be a free string, so there is nothing that is driving it. You've excited this string somehow, and we want to know the possible ways in which this string can vibrate subject to these two boundary conditions. Well, last time you learned that the general solution of the wave equation can be written as this: a sine kx cosine of omega t plus b cosine kx sine omega t. Well, let's take this first boundary condition, y equals 0 at x equal to 0 for all times. Okay, so then boundary condition number 1 says that 0 should be equal to a times, well, when you put x equal to 0, that's 0. So it's 0 times a plus b, and now cosine of kx, that cosine of kx, when x is equal to 0, well, that's going to be 1. So b sine omega t. And since sine of omega t is not 0, that says that b is 0. And so that only leaves y of xt as a sine kx cosine omega t. But now let's use the other boundary condition. So the boundary condition number 2, so I should say this is number 1 and that's number 2, that says that I must take the derivative of y with respect to x. So let me take d by dx of, there's only this over here, a sine kx, and there's cosine of omega t. Well, that has to equal to 0 at x equal to L. All right, so since a is not 0, we can just divide by it, similarly cosine. And so this gives us the condition that cosine of k into L must be equal to 0. So imposing the condition that dy by dx, that is to say the string has to be horizontal here, otherwise this ring will go either up or down with infinite acceleration. So dy by dx must be 0. That gives us this condition, cosine of kl must be equal to 0. And that says that kl can be either pi by 2, or it can be 3 pi by 2, or 5 pi by 2, or in general 2n plus 1 by 2 pi. So now what we have is the allowed values of k. So those which fulfill this boundary condition, and of course the first boundary condition is always fulfilled by this solution. So the values of kn are then n plus a half pi divided by L. And if you remember, omega is equal to V times K. That is the requirement that comes about when you put this into the wave equation. And so that says that there will be several different frequencies because there are several different values of K. So the first frequency, let's call that omega 0, will be V times pi by 2 L. And then omega 1 will be 3 times that. Omega 2 will be 5 times that. And so you see, many different possible modes are possible subject to these boundary conditions. Now, earlier on in the previous lecture, you had seen the solution where this end was fixed and this end was fixed. Now you've seen a situation where this is fixed, but this is not fixed, so it can go up and down. Perhaps now you should think about how to solve the problem where both ends are open. So where you have both ends being loose. So this is loose and that is loose, but I'll leave that as a problem. I'm going to talk about the concept of wave impedance. Now, you're already familiar with the concept of impedance, or rather resistance. The two are very similar to each other. Resistance is the voltage applied, let's say across a wire, divided by the current that flows as a result of applying that voltage. So you apply a voltage, divide by the current that flows as a consequence. In the case of a wave, we have a force that's shaking one end of a string up and down, and we define the impedance of the string as being the force that's applied divided by the velocity where you apply the force. So this is a quantity that it will be different from string to string. And let's see how this works out. So we have some long string like this, and we shake it at one end. Let's say that we shake it at the point x equal to 0. So this is the x direction. This is the y direction. We're shaking the string here for now. And the string has some, so it goes like this, up and down, but a small portion of this is going to be straight. Let's call this angle over here theta. Let's call the tension in the string T, and the tension is the same throughout the string. That means that there's a component of this force, of this tension, in the y direction. And if this is theta, this is 90 minus theta. So the component of the force in the y direction will be T cosine of 90 minus theta, T cosine 90 minus theta, which is the same as T sine theta, and that's approximately the same as T tan theta, where this holds only if the angle theta is small, that is to say for small values of theta, small amplitude oscillations. And that's, of course, the derivative dy by dx at the point x equal to 0. Now the force that's being applied is downwards. It's in the opposite direction of the tension. So if you focus your attention upon this one little particle over here, okay, it's going to be pulled by the string here and by the force here. The two are opposite. And so what we have is that F is equal to minus t dy by dx at x equal to 0. Now this is the force, and this force will depend on time. This y is the propagating wave, and let's now calculate z. So the applied force will be F naught. Let's say we make it vary as cosine of omega t. The possible solutions of the wave equation, well, anything like sine kx minus omega t or cosine kx minus omega t will do. So y of xt is a function of both x and t. So if the y is the displacement in the vertical direction at any point x at any time t, that you can write as y naught sine of kx minus omega t. And you should think about, should I include a cosine over here or not? Well, the answer is no, but you can easily figure out why that is the case. So now let me put f in here and y in here, and let's see what we get. So we get f naught cosine omega t is equal to minus t, and now I need to take d by dx of y, and y is here y naught sine of kx minus omega t. And I will differentiate this. So when I differentiate sine kx, I get cosine kx. And then I need to put x equal to 0 because we're only looking at this point over here. So this is equal to minus t y naught k, and here we'll have cosine of omega t. So we have then on both sides cosine of omega t, and so y naught is equal to f naught divided by t into k. Now, that's the amplitude. And so this is f naught. That's the applied, so the force applied divided by the velocity that comes about, or the speed that comes about actually. And so this is t. And now you remember that k is equal to omega over v. And so this is this was the amplitude that comes about. Let's now calculate z. So z is the force applied, which is f naught cosine omega t. Here the applied force is f naught cosine omega t, and the velocity, we have to calculate that. So that's velocity is y dot. In other words, it is dy by dt at x equal to 0. And let's now put this in. So z is, if I take dy by dt, then from here I will get cosine. So I will, let's see what z is coming out to be. This is f naught cosine omega t divided by, now if I take dy by dt, that gives me y naught. If I differentiate this, cosine of kx minus omega t. Now I've differentiated, and so I've got minus omega out over here. And when I put x equal to 0, I'm simply going to get cosine of omega t. And now y naught, I had a minus sign over here. You saw that. I missed that. So here we had f naught cosine omega t was equal to this. So y naught was equal to minus over here. So there are two minuses, and those minuses will cancel out. So this will give us f naught divided by omega, and for y naught I'm going to put over here f naught divided by t times k. So this is now k over omega, and there's a t at the top. Now k over omega, you recognize what that is. Omega is equal to Vk. So this is equal to T divided by V. We've got Z as T over V. But you remember that the velocity V is square root of T divided by rho. And so the final answer is that the impedance is the tension in the string multiplied by the density of the string. This says that different strings are going to have different impedances. So in other words, if you take a string and you move it up and down, well, the speed that you will get. So remember, come back to this, that Z was defined as the applied force over the velocity that results. And you see, this makes a lot of sense, because the greater the tension, the greater the force you will have to apply for a fixed velocity. And the heavier the string, so rho is mass per unit length, consequently Z will also be greater. Anytime you get a result, you should check it to see if it makes sense. That's all for now.